forgot my paper again. Okay, here we go. So, theorem 2.5.4, oh yeah, this is section 2.5. In this case, it says we have a coefficient matrix for inequations and unknowns. So, we can say let A be the coefficient matrix of a system of inequations and unknowns. Then if A is non-singular or invertible, then the system, the matrix system, you just say system. Now, I would write it this way. The book writes AX equals B. Now, and actually, that's perfectly fine. You could have sort of this multiple system, multiple right-hand sides to a system of equations, right? I want to solve the same system of equations multiple times for different sets of data. And if that's the case, well, then you might actually think of sort of setting up these matrices that have more than one column. However, in this theorem, I don't think that's what they're really getting at. I think they're getting at, because they say the system of inequations and unknowns. So I don't know. I'm not sure if they're really doing this in great generality, or if what they really meant were, one column vectors. It doesn't really matter. It doesn't change the result nor the proof. But it says then the system, AX equals B. And again, you could be thinking of it this way, or you could be thinking of it that way. Has the unique solution, and I'm going to write it both ways here. So X equals A inverse B, or again with the bigger matrices, X equals A inverse B. So that's the that's the big deal. That's the punchline, is that if your coefficient matrix is non-singular or invertible, I can compute the unknowns X simply by multiplying whatever's on the right-hand side by A inverse. So that's pretty nice. Okay, and the proof that they do, they do the two separate parts. So see, they say it's a unique solution. Well, it's unique and it's a solution. So first they talk about uniqueness. Okay, you might be able to hear my grandson laughing upstairs. That's always a good thing. Uniqueness. So they say, well, assume AX equals B. So now we're using their notation. And then multiply both sides by A inverse. And okay, so we do that. Now, actually, I don't know that I agree with their proof here. Not that what they're doing is wrong. I really think this is just really getting at existence again. So this is I, X equals A inverse B. And so X equals A inverse B. Now, see, that this, I think, shows existence. They're just multiplying through by A inverse. We know A inverse exists because we said so. So assume AX equals B. I've got my little dog getting upset with the big dog because the big dog laid on her. So, okay. So I really think, I don't know. My opinion is that really they're just showing existence here. So typically for uniqueness, and we've had a proof like this already in this section, is, I would say assume X and Y solve AX equals B. Now, looks like you've got the X here and the X there. Those are two different X's. This is a particular X and a particular Y, and this is the general statement of what we're doing. Because then, I would say something like, so here we're saying we have two different solutions. Well, suppose we have these two different solutions, and then I take A times X minus Y, right? That's AX minus AY, and that's B minus B, which is the zero vector, or, well, zero matrix or vector in this case. Okay, well now we have that, so A times X minus Y has to be that zero vector. Now multiply A inverse times both sides. And we get X minus Y. Oops, forgot my A inverse here. Yeah, let me erase that. Oops. There we go. A inverse zero vector. And so now X minus Y is the zero vector, which means X is equal to Y. Okay, that looks like uniqueness to me. As I say back here, this is their proof for uniqueness, but I really think that's an existence proof because I'm showing that I can get it that way. Now, their existence proof, they say, well, existence. They say let X equal A inverse B. Okay, so they have that. And then they say, well, AX is equal to A times A inverse B, which is equal to A inverse B, which is I times B, which is B. And see, they're saying, see, look, it solves that equation. And That's fine by me. I think that does show existence, so I agree with them. That is an existence proof. But back here, I really think this is an existence proof. Um, I, I really don't see the uniqueness exactly. Uh, I guess, what they're going with the uniqueness is we know that A inverse is unique, right? So B, of course, is set, so that's unique. And so I guess they're getting at uniqueness because A inverse is unique. Um, and and so I might go so far as to say that what they did here, then if you look at it that way, is both uniqueness and existence. Um, but at any rate, again, I see what they're doing here, and I suppose one might argue that, by starting here and then showing that it is a solution, is that existence. Um, However, here it is existence because I have A exists and B exists and A inverse exists, and so we see that this A inverse times B will exist, and therefore X does exist. So um, I think, there's that existence, the uniqueness. They don't really say it, but I think they're getting that uniqueness from A inverse. Again, typically, with a lot of uniqueness things, we'll assume that if we'll assume this is a proof by contradiction, right? That we mentioned earlier in a video. I assume the opposite. I assume that there are two solutions, at least two solutions, to this AX equals B. But then I show that they're really the same solution because if there are two solutions, then I end up saying they have to be equal, and so it's it's if I say there are two different solutions here and here, X and Y, so two different solutions, then that's where it's a contradiction to come up with they're equal. So there can't be two different solutions. You get this equality. Um, so that's theorem 2.5.4. And the big deal is that you can get a solution simply by multiplying by an inverse. Now, that's not usually the most efficient thing to do, finding the inverse first and then multiplying by it. It's more efficient using the Gauss-Jordan reduction and so forth. But symbolically, yep, this is a great thing. All right, so that's our theorem on solving equations.